Today we'll pick up and look more at cyclic groups, and particularly we'll begin looking at an infinite cyclic group, the integer, and then we're going to look at the structure of Z. So the group is the integers under addition. So in this case, let's start with the cyclic group generated by 1. Remember, this is n 1 to itself n times for any value of n would be the elements there. And also, remember, we're allowed to take powers of the inverse of an element as well. So you have all possibilities of that. So that's going to give you any integers. So this subgroup is really m times 1, where m could be any integer by definition. But that's exactly Z. So this is cyclic under addition. It's an infinite cyclic group with generator positive 1. It would also be generated by the cyclic subgroup generated by negative 1, as well. And those are the only two integers that would do it. What is a cyclic group generated by general K? It would just be all multiples of K and all multiples of negative K. So all integer multiples of K. So that's the cyclic subgroup. What about 2? That would be 0 plus or minus 2 plus or minus 4. Those are all the even numbers. So they form a subgroup. Do the odd numbers form a subgroup of the integers? And certainly not, right? They're not closed. I think they are closed under the inverse. The inverse of, say, 5 would be negative 5 under addition. But 5 plus 5 would be 10, which is not an odd integer. So it's not closed under the group operation of addition. So this is a subgroup, too. So that's in general what a cyclic subgroup is. Of any integer will generate a cyclic subgroup. We also just note, just by the definition, the subgroup generated by D is the same as the subgroup generated by negative D. And that's a general property. Any cyclic subgroup generated by an element will also be identical to that generated by the inverse of that element. Because that's, after all, how you form a cyclic subgroup. You can take all powers of the group element as well as all powers of its inverse. Are there any finite subgroups of Z? Well, one would be the subgroup generated by the identity, known as the trivial subgroup, just containing 0. That's a subgroup that only has one element, but the rest of them would be infinite, right? As long as K is a non-zero element, we'll get infinitely many different multiples. And I proved that in the notes. That's why you can kind of look at this idea as to why, if you just took a x some n times d, but you could write that as negative n times negative d. So any element x that's in this subgroup would have to be in this subgroup. And then the reverse conclusion would be true. And like I said, that is a general property that for any cyclic subgroup generated by an element, that's identical to that generated by the inverse of that element. So far it looks like most of the subgroups are cyclic. Are there any that are not cyclic? And so my claim is that that any subgroup of Z is cyclic. So there exists an integer with H being. So what that's saying is the subgroup structure of the integers, every subgroup is a cyclic subgroup, and it's generated by just multiples of a particular integer. So let's show that. And again, I proved this in the notes, but let's get some ideas. So let's handle a special case. I would put, if H is just the identity set, then we're done. Then H is certainly generated by the identity. So we're all set with that case. So for the rest of the proof, we need only to consider when H is not 0. When H is not the trivial subgroup that just consists of the identity. So how do we do this? And we're going to appeal to the division structure and the Euclidean algorithm, the division algorithm. So what do we have? We can just say, sometimes I like this term, W log, without loss of generality. We can assume there exists a T in H with T positive. Why is that the case? Well, if H is not 0, there's a non-zero integer in it, so either positive or negative. If there's a negative integer, say some integer S that is a negative number, then negative S would be a positive number, and because H is a subgroup, it's closed under inverses, so the inverse would be in it. So again, I put that in detail on the note. That's basically T and H and negative T and H. Again, that's because the subgroup, so an element and its inverse have to be in H. So we can assume that we have a positive element in H. And then what we're going to do is, what does that tell us? That gives us a positive, there are some positive elements in H. So we can appeal to the well ordering principle and find a least element. And then we'll try to argue by contradiction, and we'll somehow come up with an element that's even smaller than that. So, therefore, by the well ordering principle, H has a least positive integer. Call it, what did I call it here? I'll follow the notes. Let's call it D. Why not call it D? Because the D is going to be the actual generator. We'll show this least positive integer is in fact a generator. And so we'll argue by contradiction. We'll say if it doesn't generate, let's try to get a contradiction. And one contradiction would to get a smaller positive element from it. So what do we have? What I claim is D is an element of H. So the cyclic subgroup, all powers of D and its inverse, since H is a subgroup, has to be contained in H. And we have that containment. But what about equality? What if it's not? So if we don't have an exact equality, then what does that mean? That means there exists, and let me look at my notes, use the same notation, S and H with S not in D. And again, I won't put as much detail, I'll talk more than I'll write, because I've written it more in the notes. But what do we say with that S, if it's not in there, that really means it's not a multiple, right? That's what this set D is, right? It's all multiples of D. So we have the division algorithm, so we have, there exists a Q and R with, well, let's divide D into S, so we would have S equals Q D plus R, where, so these Q and R are both in integers. And what about R? Well, R is less than or equal to D minus 1. And if R is equal to 0, then S is a multiple of D, and we're assuming that's not the case. So R has to be greater than or equal to 1. And again, that comes from the assumption that S is not in the cyclic subgroup generated by D. So S is not a multiple of D, so the remainder can't be 0, so it's got to be at least 1. But what do we have? I've claimed then R is an L equals, well, do a little math, bring this over to the other side, S minus QD. So that's just bring it over, and then what do we have here? That's going to force this to eventually be in H, I believe, because S is in H by assumption, and this cyclic negative Q times D is in this element here, so this QD is an element of the cyclic subgroup generated by D, so that's also in H. So that element is there, and then so we have and D, we've already seen, is the cyclic subgroup is inside H. And then we have S minus an element of H minus another element of H. H is a subgroup, so that that difference is also in there. But that's got to be bad, right? Because then R is positive. Right? Because the assumption allows us to see that R has to be at least 1. R is in H, but R is strictly less than D, the least positive element. So that's a contradiction. So we got that contradiction, by assumption. So here's a mistake. I think I forgot to cross this. I'm glad I caught this equal sign. Let's see if that's okay in the notes. Good in the notes. The assumption was that the subgroup generated by D was not all of H. I mean, if it is all D, if it is all of H, that's what we wanted. So this assumption that it's not in H allows us to have S in H, but not a multiple. So that's where the contradiction came from. So that really completes the proof. Right, we got a contradiction from assuming H was not equal to D. We already knew that D was contained in H, so that proves the theorem. So the subgroup structure of the integers, you'd say, all subgroups are cyclic, and they're all infinite cyclic subgroups except for the one element subgroup that contains the identity. So let's look at a couple of examples of some of these subgroups. And I'm going to do the matrix table with the group G. And so that's the 6 elements, that's the identity that we call I. There's the matrix B. There's the matrix D. And then there's the matrix C. And K. So we have a group of those 6 matrices, and we produced the Cayley table. That should be in the notes, and I'll maybe refer to some of them as well. But you definitely want to take the notes. Look, we'll put it up. And see how that comes in the camera. There it is, this table right here. So while I'm talking, you probably want to be listening to this. But you can always check a calculation, and I will do a couple based on those matrices. Okay, so the first question, is G cyclic? And the answer is no. We saw G is not abelian. And we proved all cyclic groups must be abelian. So we know it's not, the group would not be cyclic. And again, an easy way to think of why a cyclic group would be abelian. Everything in a cyclic group is powers of an element added to itself, combined with itself under the group operation. So if you multiply a product of 2 elements, you've just got a bunch of powers of the generator times another bunch of powers of the generator. So it doesn't matter which order you write it, left to right, right to left, you would get the same total number of powers of the element lining up, and so that's why a group that is cyclic is abelian. But what is all abelian groups cyclic? I might want to think. I think we've already looked at an example that answers that no, but I believe I haven't commented on it. So what are the subgroups going to be? And we also talk about the idea of a subgroup graph. So I'm not going to formally define that. I'm going to define it by an example. We draw a subgroup graph. So let's look at the subgroup graph. And some people use the term lattice instead of graph. So at the very bottom, in any subgroup, this is always true, you just have the identity. So in general, you just have the cyclic subgroup generated by I, and that's it. That's a single element. And then up here, you have the whole group G. So in here, this is all 6 matrix. A, B, whatever it was, C, D. I think I left out E, K, I. And so we draw a line, anything that contains it, we go in here. And so you always have at least that much structure. Then what else? Well, let's look at some subgroups. Let's start creating them. Let's take A. What's the subgroup generated by A? So we start out, it's got A, and then it has A squared. And what is A squared? So if we want to look at A was, I think I've left off A on this previous board here. A, so if you look at 1, 0, 0, 1, and you square it, so what's that going to give us? That's going to give us 1 and a 0, and a 0 and a 1. That's the identity. So that's just A and I. And then we can keep going, A cubed, but A cubed would just be I times A, so it goes back around. Then you begin to, in the finite case of a cyclic group, the idea of cyclic really comes to fruition because you start with A and you keep raising it to so many times, and then for the first time you get an N where the element raised to the N takes you back to the identity, and then you would circle through those same values for the higher powers of A. So that's all here. So that's in the bottom. That contains an identity. So we maybe put that subgroup A. Now that other subgroup may not always be cyclic, so we may have to put like just a list here. Like here, I don't know if G is not cyclic, so we have to just write G. We can't, you know, or write all 6 elements. We can't write it compactly as a cyclic subgroup. So that takes care of that. And I think there are a couple of these elements where they happen. They're not the ones in the first group. Remember, when we introduced this group, we really had, I think, B and D were kind of separate. But I think C squared is also the identity. So if we look at the cyclic subgroup generated by C, so that would be that. And then if we square it, so multiply that by that, you would get, here it's going to get a 1, and then this would be a positive 1, minus 1 is 0. And again, you can refer to the Cayley table that C squared is I, so that's also there. And that contains I, so we put it up in this line here, but A and C, they're not contained within each other, so we would just stop there. Then what else can we look at? Let's pick another element. How about B? So that's going to contain this matrix which is going to be, let's square it, let's just make a calculation. This is, see what B squared is. Again, we can appeal to the Cayley table. But multiply, this would, 1 here would pick up a negative 1. And let's see, B has a negative 1 here. So you would get a positive 1, and then a negative 1, and a positive 1. So, sorry, this would give us a negative 1 here. This would give us 0 plus negative 1 and negative 1 here. And then this is where it would be a positive 1, and then this would be a negative 1 plus 1 with a 0. Which is D. Seeing that B squared is D, so we would have D. So far this element has, it certainly has B, it's got B squared, which we've seen D, it's got B cubed. What is B cubed? Well, we just take D and multiply it 1 more time by B. So I'll erase some of these matrices. Again, you could be referring to the notes for the labeling system. And again, these calculations can also just be looking at the Cayley table. So if we have B cubed, that's the same as B squared times D, or D times B squared. B squared times B. B squared is D, so it would be D times B. And then on the Cayley table, D times B, I read off that as the identity. And maybe I should just check that. So here's D, and then here's B. And so if I multiply, I would get a 1 here, and a 0, and then this 1, 0 in the bottom row will have the effect of picking up the top row and sticking it here. 0, 1, which is the identity. So that's it for that element. So that doesn't contain any of these, so we wouldn't draw a line up here. We put it maybe at the next level because it has more elements, so we put it higher. So there's B, which is also the same as a cyclic subgroup generated by D, right? If you take D, you can look on the Cayley table and directly calculate D squared as B, and then D cubed would be the identity. The identity is, of course, in this, so we draw it here. So have we looked at maybe some other possible subgroups? Well, I think there's one more element we haven't listed as K. And if you look at the cyclic subgroup generated by K, so that has K, and then K squared, which, looking at the Cayley table, we can see K times K is I, and a direct calculation can show that. I'll try to multiply matrices in my head, which is a bad thing to do. If I took this, it would be against this row, so 1 times 1, 0 times -1 would give us a 1. And again, 0. This will have the effect of just picking off the top row, and then I take this, -1 times 1 would be -1, -1 times -1 would be +1, add them up to get 0. And then over here, this would be a 0, and -1 times -1 would give a +1. So we have K here. And again, K doesn't have anything in common with this, so this goes up to 8. And these doesn't matter if they cross. Make it clear that this is not contained in this subgroup. So that's kind of the notation. If subgroup H contains subgroup K, we draw a line up from K to H. So that's a subgroup graph for this. Or maybe it is. That's a partial one. Have we got everything? Are there more subgroups? So how can we get more subgroups? Well, what I propose is in each of these subgroups, let's throw something else in and see how far we can take it and see what's the smallest amount of stuff we can throw in to make it a subgroup. So let's take a look at that now. Again, I've erased what elements are in each group. But these are fairly easy. They just contain the element, the generator, and the identity. And this is not even that much. This is a 3 elements. It has a B, D, and the identity. So let's start with A. So we have A. We've got to have A, and we've got to have the identity. And let's add K to that. So we'd also have to have K. Is that a subgroup? Well, no, we'd also have to have AK, and then AK is just D. So we'd have to have A and D. But we've already seen if we've got D in it, we've got to have all the powers of D. So we'd have to have D squared, so we need to have B. Again, the assumption is we want to see a subgroup, right? As a set, we can certainly just add K, that element, to A and the identity. But to have it be a subgroup, we're going to need not just adding K, we're going to need to also add this to keep it as a subgroup. And then I think we almost have the whole group. Let's count. 1, 2, 3, 4, 5. There's a 6th element. So what's one way we could get a 6th element? You can look at the Cayley table. There must be some way to piece together this and get a C. So you can look down and you see a C in the table. It looks like B times K is equal to C. So B times K would give you C. So if you add K to A, you get the whole group. And that's basically a similar way you can say if you have a subgroup with any 2 elements, of course not equal to the identity, from 2 different subgroups among, well, what are the subgroups we're looking at? Well, there's the one generated by B, which is also the one generated by D. So any two elements from two different subgroups among those four different ones, I claim you get the whole group. And they're all proved that way. Let's take another two elements. So suppose you have this subgroup, and let's take C and B. So we have those elements. Anytime we have B, we have B squared, which is D. So we have D. Of course, we're always going to have the identity. And then what else must we have? We have to have CB. So C times B is K. So we have CB, but that's K. Can I take advantage of a different calculation? AK. BK is C. Well, we already knew that. We have C. What else do we have? Then we have DK. D times K is A. Do we have the whole group yet? 1, 2, 3, 4, 5, 6. And we have the whole 6 elements. So eventually you can work through all the ways of pairing up any two of the different 5 elements. Basically, I wouldn't say any two of these 5, because if you take important B and D, you sort of, by having B, you automatically get D. So B and D wouldn't work because those are two elements from just the same subgroup. But if you take two elements, apart from the identity, from any two different of these 4 subgroups, you will generate the whole group. Okay, and then we also note, just a couple of notes here, what are the order of the subgroup? The subgroups have order what? The number of elements in the subgroup, well, the identity element has order 1. The whole subgroup has order 6, G, and then the proper ones we have 2 and 3. And these are divisors of 6. So again, the order of the group is 6, and the order of the subgroups are all divisors of 6. So the question, let G be a finite group. A finite group with the order of G equal n, so there are n elements. And H is a subgroup of G. Does the order of the subgroup always divide the order of the group? In other words, in any subgroup, does if in a finite group with n elements, for any subgroup, is the number of elements in that subgroup a divisor of n? I think I also introduced some notation as well. So you could also think about G a group, A an element of G, this subgroup, cyclic subgroup generated by A, is the smallest subgroup of G that contains A. This is actually not in the notes, I maybe will add it, though this is kind of a bonus material that why it's the smallest subgroup. So certainly, A is a subgroup that contains A. But why is it the smallest? Well, let's take any subgroup that contains A. What does smallest mean? Smallest would mean we want to show that the cyclic subgroup generated by A is inside of H. Take any subgroup, let's give this subgroup a name, H. Any subgroup H that contains A. I don't know if I bumped into this, the camera. Somehow it's moving on me. So let's go back. Okay, so we've got that. So take any subgroup H that contains A. So what would happen there? That would give us. So let's show that this cyclic subgroup contained in A is in there. So let X be. In A, that means there exists an integer with x equals a to the n. But if n is positive, since H is a subgroup, x to the n has to be an H. And even if n is negative, then again we have a subgroup, so we're using the full force. Not that it's closed on the powers multiplication of A, but it's also got to be closed on the inverse. So A inverse is an H. So A to the n, which is A to the inverse to the negative n will be positive. So this would be an element of H because A inverse is an H and negative n is positive, so you just multiply an element of H by itself a positive amount of times, that's going to be an element of H. But A to the n, so in either case, X, which is A to the n, is an element of H. And then clearly, so that just means, well, let's see how far this goes over, but that really means a cyclic subgroup generated by H. Again, so that has moved just a little bit. So what does that tell us? Okay, so let's get back to the, now we're done with the camel work. X was a typical element in the cyclic subgroup generated by A. X has to be in H, so the cyclic subgroup is contained in H. So that, in that sense, that's what it means for this to be the smallest subgroup. And the other subgroup that contains A will all have to contain the cyclic subgroup generated. And the reason for that now, in general, we could let, again, so we have A, B, the elements in G a group. We use sort of the same notation, put a comma. This is the smallest subgroup of G that contains both A and B. So it does not have as nice a definition, right? Remember, when we just have a single element of A, this has a very nice definition. Just all integer powers of the element. But the definition is not nearly as concise where there's two elements. And this will generalize into, you could have three elements, right? You could have A, B, C, you could have multiple things in the parenthesis inside here. And you talk about the smallest subgroup that generates those elements. So just in the notation of the last example, if G equals that group of matrix, capital I, A, B, C, D, and I use K. For instance, that was generated by A and B would be one way to generate it. And you can even generate it with A and K. So G wasn't cyclic because a lot of times we'll see that groups can be generated by multiple elements. A cyclic group is generated by just a single element. And then in that case, when you talk about the subgroup, the smallest subgroup that contains a single element, it's just going to be all the powers of that single element. Okay, so let us look at one more example, subgroup Radis, and look at another group, an 8-element group. Okay, so we're going to look at a set of matrices like QB, the following set of matrices with complex numbers. So we have the identity, we have, really what we've done is we've multiplied every entry of the identity by -1. We have a matrix that's not like the identity, kind of switch the rows in the identity. So 0, 1, 1, 0. And then again, we'll have a matrix, we'll multiply every number of that by a -1. And there's another matrix that's got a 0 and then the complex number I. And the complex number I here is off diagonals. So Q is a subset of the 2x2 matrix with complex numbers. So that I is not just some integer, subscript into it, it's the square root of -1. It's defined by the property of I squared equals -1. And then another entry we're going to have multiply that each of these entries by negative. We really multiply the 0 by negative, but negative 0 is 0 in all those cases. So we have 6 matrix, and we have 2 more which would be a negative I here, 0, and a 0 I. And then actually I'm going to move these over, so let's just, negative I, 0, 1, and then if I multiply, and then a 0 I, and the other one would be that same matrix, but let's multiply everything by -1, so it would be positive I, 0, 0, and then a negative I. And just so I don't have to keep writing matrices to fill out the table, there's well, I'll come to that in a second. So I'm asking a couple of questions. So we first want to show that it's a group. Let's do a Cayley table. So let's prove it's a group by completing the Cayley table. And to help label it so we don't have to put matrices, let's give these names. We'll call this, as usual, the identity. Okay, and this one I think I erased. Right? That's down here. So this is the identity. And then this one, we can give it a separate name, but it's really the negative of the identity. Now I'm going to take a fact, but you don't need to take this as a fact. You can do it with the individual calculations that, you know, negative B, if B times C is D, then negative B times C would just give us negative D. In other words, that negative sign, when you multiply a whole matrix by -1, you know, you can just treat it the way you would with a regular variable. And then this matrix here, I think I called it A. A would be this. Just even in the set. This is not even in the set, right? This would be a -1 here. Okay, so that's a -1. And that would be a positive 1. Okay, good, good, good. And that's correct in my notes. So that's I. So this one we'll call maybe A. And then this one would be, rather than give it a separate line, it's really -1 times A, the negative of A. And then this other one that has the I's off the diagonal, we'll call this one B. And this would be negative B. And this matrix then we'll call C, the one that starts off with a negative I in the top row and a positive I in the bottom row. And this one we'll call negative C. And so let's do a Cayley table. So we're going to need to have this one here. So this is A. So we have I, well, let's see, we'll need some name room is going to be needed down here, right, as well. So I, negative I, A, negative A. That will need a lot more room. So we'll just erase what negative B is to give us some more space once we have what B is. And then we'll jumble, maybe put B, we'll rewrite that over here. that. And then we maybe have enough space to do our Cayley tables up and down. I, negative I, A, negative A, B, negative B, C, negative C. And the top row should be the same, I, negative I. Again, hopefully we have enough room. A, negative A, B, negative B, C, negative C. And again, this will be in the notes. But I'd like to at least maybe fill in a couple of these. Okay, we already know the matrix has that property of the 2 by 2 matrices. So we already know that this and this is going to be the same. And then negative I, so it would just be I, negative I, A, negative A, B, negative B, C, negative C, and so forth down here. Negative I, A, negative A, B, negative B, C, negative C. Then what about this row? If we were to apply negative I, that's going to, the identity would just give these back. Negative times the identity would just give the negative these back. So these all switch. This would be I, negative A, negative B, B, negative C, C, and so forth down. Negative I, same with this row. Negative A, B, negative B, B, negative C, C. So far that's not too bad. Of course, no repeats. One way we tell a finite group is a group from the Cayley table, if it's like a Sudoku puzzle. If each column and each row there's no repeat, then it's guaranteed to be a group if it's associative. We take as always the associativity of matrix multiplication to be granted. So then we have A squared. What is A squared? Well, A squared I almost tried to square this in my head. This row here will pick the bottom row up and put it up top. And then this will pick 0 here, and that will put a negative sign there. Will give us the negative identity. So A times A is negative I. And again, we may want to do a subgroup lattice, right? So while we're here, this might be a good time to start making some notes of some subgroups, which I did here. So what is the cyclic subgroup generated by A? Well, it certainly has A. It's got A squared, which is negative identity. It's got A cubed. A cubed is just on A times the negative identity, which is negative A. So you would have negative A and then A to the 4th would be A times A cubed, which is A times A cubed is negative A, so it would be A times negative A. Well, A squared is the negative of A identity, so A times negative A would be negative A squared, it's just the identity. So we have those 4 elements. Again, that's coming on because one thing we're going to look at is look at the note, we're going to look at the center of it, and we're going to be thinking about the subgroup lattice as well. We'll maybe come back to that in a second. So then A times negative A would just be the identity. What about A times B? So A times B, there's A, there's B, so what would that do? Would that be, now that I'll erase A cubed, AB would be this would have the effect of move the top row up here, and this would be 0 and 0, and negative I would be I, negative I. I believe that's one of our entries. I think that's negative C. So A times B would be negative C. Then what's A times negative B? That should just be the negative of A times B, which is C. And you can directly calculate these with the 2x2 matrices. I'm just appealing to the fact that basically for a matrix, negative x times y, x and y in matrix is the same as the negative of x times y, or x times negative y. So that multiplying a matrix by a scalar, I'm using that property of how that behaves. Then we have to do A times C. Well, if it's going to be a Cayley table, best be B, right? Because otherwise we have a repeat. So let's see what A times C is. A times C is just A is this matrix. C would be negative I, 0, 0, I. And so this will pick the bottom row up and put it in the top row, and then this will take the negative of the top row and put it in the bottom row. And that's something, ain't it? Yep, that's maybe erase, that's B. And if AC is B, then AB should be negative C. Sorry, A negative C should be negative B. And then again, once we have the row across for A, the row for negative A, we don't have to take this property about how the negative sign behaves with matrix multiplication. We could do all the individual calculations, but it's going to work. And so it'll just be the negative of this row. And now we move through and fill out a couple more rows. So it's really the calculations are not too, there are shortcuts to calculations using some of the properties of matrix multiplication. So let's look at some more calculations. BA, so BA would be this, and then A would be 0, 1, and 1, 1 here. So that would give us a negative I and 0 and I, and that I think is exactly C. So BA is C, which is good. It shouldn't have been A because we can't have any repeats. And so far, everything looks good in terms of the group. Appears to the Cayley table is trying to prove it's a group. So we're proving it a group by just brute force, showing that we have a Cayley table. And as we've explained before, if there's no repeats and for finite case and down each row and each column, if you can take associativity as granted, that means you have to have inverses and you have to have closure. And you'll have all those group properties. And so then if BA is C, B times negatives A would just be negative C. And then B times B, B squared, this will be important for the, when we get into the cyclic subgroups, and we analyze its behavior, the subgroup graph here. So that would give us a positive I squared, which is a negative 1 and a 0, and that would give us a 0 and a positive I squared, which is a negative 1 there. And that's something, right? That's the negative of the identity. So B squared is negative I, so B times negative B is just I. And B times C better be A, otherwise we're gonna otherwise it wouldn't be a group, it'd be a repeat. So let's make, but again, we're not assuming it's a group, that's what we're trying to prove. So let's look at a B, and then C is that matrix with a I up here, and a negative I, and a positive I here. I shouldn't say that, it's possible it could be negative C, a negative A. So we would get, that's a 0, and that's an I squared, which is negative 1. And then this would be negative I squared, so that would be negative I squared is a positive 1 and 0. So that is something, is that A? That's actually negative A. So that would give us negative A. And then if B times C is negative A, B times negative C would have to give us positive A. Not positive A, but just A. Again, maybe really, I shouldn't really say negative of a matrix. I really should be saying negative 1 times a matrix or versus positive 1 times a matrix. I mean, we're not really thinking of negative positive in the usual sense how it would apply when dealing with real numbers. But so I apologize for that. Really, that negative A means I mean to say negative 1 times A, and A or positive A I should be saying positive 1 times A. And then what else? Then once we have the B, then negative B should be just the opposite of all these. And so we're done. We'll come down the home stretch, just a couple more calculations. CA, and again, so far no repeats down in every column. So let's look at C times A. So CA, C is negative I, 0, 0, I, and then A is just the 0, 1, negative 1, 0. And that would give us, that's going to give us a 0 and a negative I, and a negative I, and a 0. I think that's a negative of one of these matrices. There's B up there, that would be the negative of B. And if C times A is equal to negative B, then C times negative A would be equal to B. And that's CA. Now what about CB? Let's look at C times B. So C times B would be, where is C? I haven't raised C yet. Negative I, 0, 0, I, and B would be 0, I, 0 here. So I'd multiply, that would give me a 0 and a negative I squared, which would be a negative I squared, which would be positive 1. And then this would give me 0 and I squared, which would give me negative 1, and then a 0 here. So that's one of those matrices, is that A and negative A, that's equal to A. And so if A times B is equal, if C times B is A, then C times negative 1 times B would be negative 1 times A. And so if we're going to have a Cayley table, we've got to have either the identity or the negative, or negative identity in one of these two spots. Let's maybe clean up. We don't need to, let's minimize the matrices we write, maybe put them on the board here. So we don't need to say what B is. A is 0, 1, negative 1, 0. B is 0, I, 0. And and C, which I've just erased, was negative I, 0, 0, I. And so what the heck am I doing? C times C, right? C squared. So C squared, negative I, 0, 0, I, negative I, 0, 0, I, positive I squared, which is negative 1, 0, 0, positive I squared, which is negative 1, negative identity, the negative 1 times the identity, and then C times C is the negative 1 times the identity. C times negative 1 times C would just be the identity. And then once we've got the column for multiplying C, the column for multiplying negative 1 times C, we just multiply each of these matrices by negative 1. And so we have a Cayley table. That was one question. There's so much space in the matrix, I just stated it. It's in the notes written first, but show that, assume an associativity for matrix multiplications, show that C is a group by exhibiting the Cayley table, and then you can prove it's a group because it's closed, it's got inverses, and that's all we need. Then the next question I asked is find the center of Z. Let Z of Q be the center of Z, a center of Q, which is all X such that it's all matrices such that X, A equals AX for any A in Q. So I think at the end of the last videotape we left off with the center, we talked about the centralizer. That was you had to be given an element. So the center, those are the elements that commute with everything. So what is Z of Q? Well, in any group, the center is always a subgroup, so it always has the identity. And if one commutes with all of the, if the identity commutes with, if the matrix commutes with anything, then its negative would also commute with anything. So negative I. So those two matrices, and that's it. Why is that it? Well, is A in the center? Well, let's look. A times B is negative C. B times A is positive C. So that means A and B can't be in the center because A doesn't commute with B, so A can't commute with anything. And B doesn't commute with A, so B can't commute with everything. I didn't say A can't, not that A can't commute with anything, A doesn't commute with anything. So we can't have A and B are in the center, and we've just seen if a matrix commutes with every matrix, then negative 1 times that matrix will still commute with all those matrices, so negative A, negative B also can't be in the center. But maybe C could be in the center, but I think that's not the case either. C times A is negative B. And will A times C be enough to get me A times C is positive B? So C can't be in the center, and then certainly its negative can't be in the center. So the center of Z is exactly those two matrices, the identity and then negative 1 times the identity. And then the last thing I want to do is look at the subgroup graph. So let's start by looking at the subgroup. So right down here we have the identity. And then up here we have the whole group Q. So let's look at, start small. Cyclic subgroup generated by the identity, that's always just the identity. What about the negative identity? Is it the same cyclic subgroup? Well, let's see. The negative of the identity squared is just the identity. And so the cyclic subgroup generated by the negative identity is just a 2-element group. What about A? I think I started to work on A earlier on a board. At least initially we had A. We had A squared, which I think I calculated that A squared was negative I. Then A cubed, well, if that's A squared, if I multiply negative 1 times I times A one more time, I would get negative 1 times A. And then if I multiply A to the 4th, that would be A cubed is negative A, so it would be negative A times A, and that's just the identity. So that's a subgroup, and that does contain this, so I would put maybe here. And now I'm not sure, there might be something in between here or not. We'll see. What about B? Let's look at what B generates. So we have B, and then B squared. B squared is B times B, which is negative I. And then B times negative 1 times the identity is just, or shortly, B times negative I is just going to be negative B. And then B cubed, B to the 4th, well, B cubed is negative B, so B to the 4th is just B cubed times B, or negative B times B, which would be the negative of B squared. We've already seen B squared is negative of I, so the negative of B squared would be positive I. And none of these are in common, so we draw a separate line up here. And again, these go up here, but I can draw these lines, but maybe I may need to erase to put some more subgroups here. I don't think here there's really nothing I could add, right? If I've got this subgroup, if I add B to it, then I've also got to add negative B in. I'm already right up here. So what's left, I think just C. So we have C, and then C squared. Well, C squared be I. C squared is negative I. So C cubed would be the negative of C, and C to the 4th would be negative C squared, which is negative of negative I, which would be positive I. So again, the subgroup diagram would look like that. Maybe. Anything missing? Well, let's see. Let's start adding stuff. And maybe now I can erase this Cayley table. Also, I point out, what are the order? Remember, this is the order. The order of these three cyclic subgroups is 4. And there are 8 elements in Q, so 4 happens to be a divisor of 8. Again, that's a question we want to see, is that true in general for finite groups? And then the order of the subgroup generated by negative I, that has 2 elements, which is also a divisor. So anything else? Well, clearly if we add A to this subgroup generated by negative I, we're not going to get a new subgroup. We just get all of A. And same thing, adding B to that subgroup. If you want to look at the biggest subgroup that has, find the biggest subgroup that has negative I and B, well, that's going to be all of B and C. So there's nothing to add between here, right? Because once we add one of these 3 elements, or the negative of one of these 3 elements, to this subgroup, if we're going to still have a subgroup, we've got to end up with this group if we add C, this group if we add A, this group if we add B. But what about other groups? What if we have A and B? So what if we add B to the cyclic subgroup generated by A? Well, I just erased the Cayley table, but I have one in my notes, or you can show a direct calculation. We've seen that if B is in A, then we have to not only have B, and we would have to have AB, but AB was negative C. So not only would we have B, but we'd also have negative C. So we virtually have almost the whole group, right? Would we have to have C? If we look at BA, we'd also have to have B times A. So that would give us positive C. And then again, if we have B, we're going to certainly have all the powers of B, so we will have all these things. So no, you get the whole group. And a similar argument can show if you added, that also shows that if we add B to this subgroup or A to this subgroup, we'd have it. And same with adding either A or B to C to this subgroup would take us all the way to the whole group Q. So that's it. That's the complete subgroup structure of this. And so we'll close with just a little note. All proper subgroups, that's all subgroups except for the group itself, of Q are cyclic. But Q is not. Right? Because we've looked at, for all of the elements, we've looked at this. And I should point out, actually, I did in the notes, that this is not true for the identity, but the cyclic subgroup generated by the negative of A is the same as the cyclic subgroup generated by A. And the cyclic subgroup generated by B is the same as the cyclic subgroup generated by the negative of B. And the cyclic subgroup generated by C is the same as the cyclic subgroup generated by the negative C. But again, that's not the case here because the cyclic subgroup of the identity is just the single element group. So we'll close here.